the last chapter, right, we kind of looked at analytical ways that we could solve 2 degrees of freedom. I mean, we did introduce some matrices and a little bit of linear algebra. But even when we looked at that last problem, right, so the one where we're taking, you know, the D1, D2, DS, you know, that gets incredibly complicated to solve, right, and isn't really very useful. So what we can do then is kind of turn to some more linear algebra tricks, particularly in modal analysis, and we can solve these situations much easier. But to this point, all we've really been doing is solving for the time series response, right? And we're going to do that, but we need to think more about what systems do we actually want to model, right? So I'm hoping on Thursday we can model an airplane wing. That's my goal. And then we can reconstruct the displacement based on, you know, a certain level of accuracy that we want, right? So if you want to model something, you know, you might have a physical structure that you go out and test, right? So you can have an airplane wing, you go out and you get your first couple mode shapes. So hypothetically, anyone want to guess, you know, like how many mode shapes can you get from a structure? Yeah, like 3 to 4 to 5, maybe 10-ish, something, right? But like if you have a finite element model, how many degrees of freedom could you model that structure with? Yeah, right? So you could have 100,000, 200,000, right? If you have 200,000, how many eigenvalues do you get? You get 200,000, right? If you have 200,000 degrees of freedom, you're going to get 200,000 eigenvalues and 200,000 eigenvectors. So you technically have the 200,000th frequency of that structure, right? It's useless. It doesn't mean anything. So how many frequencies then do you need if you wanted to, say, build a time series displacement of this system? You know, how many frequencies might you want to use? 2, 3, 4, 5, something like that, right? Depends how much kind of computation time you have and how do you get your excitation. And then how accurate does that get you, right? So maybe the first 6 frequencies gets you, you know, depends how you quantify your metrics, 90% of the way, 95% of the way. If you're ever doing anything in life, you want to be the person doing the work and the person defining the metrics and how you grade yourself. That's what you want, right? So we need to think about these continuous systems and how we model them. So what we can do is we can model a system for a given number of modes. So let's say we have a system, right? And our system modes, you know, are 1, 2, 3, up to like, let's go 600, right? But we only can really measure these, right? So we can rebuild, you know, the system with these modes. That makes sense? Not perfectly, right? We're gonna lose some things, but we're gonna truncate our system down, and we're gonna do that using modal matrices. So we also have to look at the concept of spaces before, right? So before we've had a time series space. I think we kind of did a figure like this, right? We have a time series space. It's kind of one-dimensional, and then we had a complex space when we talked about Laplace, right? And we would go back and forth between our complex and our time series. And we're going to do the same thing here, but now we're going to have a physical space. So maybe we have right, we have, this is my imagination of springs. Maybe we have a system like that, connected to a fixity, then connected to each other. And there's this 8 degrees of freedom, right? I would see this as going like that, right? 2 degrees of freedom, 1 on each block. So that we have a physical space. So what we want to do is transfer this into a modal space. So where we have modal coordinates, right? So here we're going to have, you know, x1, x2, right? And here we're going to have modal coordinates. Like R1, R2, which we won't talk about today, and maybe we'll talk about on Thursday. But the modal the modal space is going to be, you know, maybe our first mode shape looks something like this, and our second mode shape looks something like this. That makes sense? So we're out of the physical space and kind of into the modal space. And then we can transfer here and here using S and M negative 1/2. And there's other ways we can transfer in between those spaces, right? But those are the two things we want to think about. So today we want to, what we want to do is we want to start in our physical space, right? We want to go down to our modal space. We want to select some of the modes that are important to rebuilding our solution. We're going to solve for those modes and those participation factors, which we've talked about before, or referenced before, but not really talked about. And then we want to come back to the physical space. And by coming back to the physical space, then we can replot our time series displacement. How's that sound? On a scale from 1 to 10? 9, pretty good. Okay, so let's go ahead and get started. So that's kind of our general overview of modal analysis, right? So let's go ahead and consider the linear system mx double dot plus kx is equal to f. I'm going through a midlife crisis. I'm going to try to start denoting vectors with arrows on top of them. So M is a matrix, X is a vector. The arrow tells you it's a vector. That makes sense? The math is getting hard, and I think that'll help. Right? So you're not confused on what's a scalar and what's a vector, because we're gonna jump around a little bit. Okay, so before, when we wanted to solve for eigenvalues, what we would do is get a mass normalized stiffness value, K tilde, right? Which was M negative 1/2 K M negative 1/2, right? And then we would take the eigenvalue of K tilde, right? We could do that in MATLAB. So this works. The challenge here becomes scaling of your matrices, right? This is a simplification, so we're going to drop the simplification and just solve the generalized eigenvalue, right? If you solve this and the way we're going to do it, you get at least in MATLAB or Python, and Python is how I did it, you get the same eigenvalues, you get different eigenvectors, right? But eigenvectors are just directions, so you have to normalize them, but we're just going to solve it in the general form because it's cleaner. So the generalized eigenvalue problem right, is going to transpose one linear matrix onto another. So these two matrices will become exactly the same. But to get one matrix to be the same dimension as another matrix, you're going to have to, transpose it. So you need directions. You need directions, which are your eigenvectors, and you need amplitudes, which are your eigenvalues. So we're going to end up with lambda mv. So eigenvalue mass matrix eigenvector is equal to k times our eigenvectors, right? And so the challenge becomes getting the correct matrix of eigenvectors and the correct matrix of lambda, but lambdas are just on the diagonal. That makes sense? So nothing there is a vector, I do believe. They're all matrices. And then, of course, how do you do that, right? You do that in MATLAB or Python. So for a n degree of freedom system, right, so we are solving for a n degree of freedom system. Right, so for the nth degree, I instantly don't like that. Let's go for the ith degree. And let me need a note to fix that. I mean, the nth degree works too, but I feel like it's more prudent to say for the ith degree. Okay, so for the ith degree, we can break this system up into this linear expression, which is omega to the I, so the natural frequency of the mode we're worried about, squared, times our mass matrix, times our eigenvector I, it's a vector, so it gets an arrow, equals A V eigenvector. That makes sense? Right? Oh, what am I missing? I'm missing an I. Right? So now we went from our matrix of eigenvectors, which was this V here, to our eigenvector. Right? We have an actual vector. So a 20 by 1, or if you do that, or 20 by nothing, right? You have an actual vector. All right, so let's go ahead and think about our n degree of freedom system, right? Our n degree of freedom system, if we want the displacement, what's the variable that we want to solve for? What do we want, Nylid? What's the variable we want to solve for? Yeah.
No, it's
Nerlev, sorry.
You said our n degree of freedom system, and you said what you want to solve for?
Yeah, so what are we trying to solve for?
I would say the natural frequency omega.
So we want to know, so when we set up the problem, right, we want to solve for our displacement. That makes sense? So we're going to go into the modal space, we're going to truncate our system and bring it back out. And we're trying to solve for the displacement as a final thing. Right? So our variable for displacement is, no, for displacement. Yeah, right? So we're going to go x, and it's a vector, right? Because maybe we have a system that's like a plane wing, right? And we have lots of degrees of freedom down, and it's x1, x2, x3, x4. That makes sense? So we're solving for a vector of x, yes.
So when you say you're solving for your displacement x, is that purely associated with the mode shape that you're looking for?
No.
Or is it the overall?
No, is x in the physical space or the modal space? Physical.
So it's not associated with that omega I that we're solving with.
No, your omega I is your, what's omega I?
The frequency of the mode that we're interested in.
Yeah. This is an x of I, right? This is a vector. So you're going to have a vector for displacements for each degree of freedom. That makes sense? So again, we're trying to solve for our physical displacement. And to do this, we're going to go down into our modal space and get a solution and bring it back. And in the modal space, we can truncate degrees, modes that we're not interested in, right? Because if you go to a testing laboratory and you want to get a time series response to measure fatigue life on the wing of an airplane, right? How do you do that? You can do that statistically, but that's no fun. No one trusts the statistics, right? That's why those people make a lot of money and give you huge uncertainty. So you want an actual displacement so you can measure fatigue and do your Paris law, things of that nature. So you're going to come down into modal space where you can actually gather data and then bring it back out. But you can't bring it all out, right? You can only really bring out the first 10 modes. Let's just say 10 for kicks and giggles. Yeah.
I was gonna say, how do you know which ones to truncate? You said after 10, you truncate.
After 10, you just can't measure them. They get really hard to measure, right? And then they fall into the noise. And also, you have to have an understanding of how the system responds, because you have to know where to put your accelerometers. That makes sense? And so there are things like laser vibrometers, right? You can take a laser and you can shoot it at a panel and you can move the laser around. You can get the displacement at a very fine resolution over an entire structure. It just takes hours, right? So yeah. So again, you know, we live in a physical space. We want to come to a modal space, grab our frequencies of interest, and pull them back out. Does that make sense? From a conceptual thing. So this is x of t, and it's a vector, one for each of the degrees of freedom that we're considering. Okay, we have a linear system, right? So linear systems means we can add these together. So let's get our temporal response. So x of t, which is a vector, is equal to q1 as a function of t times v eigenvector 1, right? So is q a scalar or a vector? Scalar. It's one value at a given time t. So q is going to change over time. Q is our participation coefficient, participation factor, participation value, principal component. You can name it any of those. I'm going to go participation coefficient. Even though up to this point in the class I've used the word factor, I think coefficient's more correct. All right, plus Q2, the coefficient, participation coefficient of our second mode as a function of time multiplied by our second eigenvector, which is related to the mode, plus however many you want, Qn of t eigenvector n, right? And if you consider a 1,000 degree of freedom analytical solution, right? So if you build your mass matrix for 1,000 degree of freedom, you could take this out to 1,000, right? And then you just hope that, you know, your Q's at the end are so small that they don't participate, and then you can drop them, right? So you're going to get most of your energy in your first couple of Q's, in your first couple of modes. That makes sense? That's why when you see a light pole flex, you only see the first mode, right? Now that you've talked about it enough, you might look for the second mode, and you might be able to see it. Sometimes I think I can see it, but I think I'm just going crazy. But you can't see the third or fourth or fifth or sixth mode, right? You know, and some of those modes are going to be like torsional around the pole, and like it's impressive. You're never going to see it. Does that make sense? So again, we're interested in the first few numbers, right? Like this is what we want. All right. Now we get into the part that's a little weird. We need to define a modal matrix, right? A modal matrix. And that P is equal to our eigenvector 1, eigenvector 2, eigenvector n. All right? So despite the fact that we kind of define this the same way, it's not equal to the matrix of eigenvectors, right? And this is my fault. I've been thinking about this a lot. I don't know a good way to do it yet. We have to scale these, right? It's not equal to our eigenvectors because we have to scale them. Remember our good term alpha from before? We were scaling eigenvectors, right? The eigenvectors only contain direction information. So we can scale them however we want, and we still have that direction information. But we have to make P to get orthogonal eigenvalues, right? So we have to scale these, yeah.
Does that mean the modal matrix is directionally equal to the eigenvector?
Directionally equal, yes. Magnitude equal, no. Right? And the interaction between the eigenvectors is kind of where we're having the challenge. Does that make sense? Yeah. And like I said, you know, like a lot of this is just kind of done, you know? So, you know, the books just kind of give it to you. But if you don't think, at least even if we don't get every aspect of the linear algebra, right? If you don't get it, just think about how the data flow is going through this problem. Right? So we have an eigenvector, sorry, we have a modal matrix. A modal matrix allows us to go from the physical space to the modal space, right? Our little magic donkey that we can ride through space. I don't know. Horse. It's the tool that allows us to transfer from our physical to our modal space. So that gets super exciting because you can just write that as x vector of t, right? Again, this is going to be all of our degrees of freedom, is equal to our modal matrix times our Q vector as a function of t. And what's our Q vector going to be? What's Q? Jude, Q?
Our participation coefficient.
Yeah, participation coefficient. In a way, the amount of energy that the mode has. Energy used in a very broad, non-technical sense of the word. Like when your friend says, I'm getting some good energy from this place. That kind of energy. That makes sense? Not units of anything. Yeah.
So the participation coefficient wasn't a vector in the displacement above. I was wondering why it's a vector here.
How many participation coefficients do we have?
Well, above it was like as many as you want.
Yeah, but each one is a scalar, right? So we're going to go with, you're absolutely correct. Q vector is equal to Q1, Q2, Qn. Does that make sense? So yeah, you're absolutely correct. The Q up above was individual components, and this Q is a vector. You see why I'm going with the arrows? Yeah, or this would be a disaster. So, yeah. Okay, so, and again, this is the same information, right? X of t is our modal matrix, which contains our normalized and orthogonal, our normalized and orthogonal eigenvectors, multiply by a vector of our participation coefficients. Right? Let's forget damping, because that's hard. So we're going to go with x vector of acceleration is equal to p q vector of acceleration t. That makes sense, right? This is our acceleration term. All right. We have an acceleration term and a displacement term. What have we always done with these? Yeah, someone over there said, who said that? Yeah, into the equation of motion, right? Okay, I get the vibe. Maybe I should speed up a little. So MP Q vector double dot of T plus KP Q vector of T is equal to F vector, right? We have an excitation at each degree of freedom. If we only have one excitation on the system, it's just going to be a sparse vector. Mainly 0 is probably 1 value. We want to convert this into standard form. Not actually an easy thing to do right now, right? So what we're going to do is we're going to multiply. So to convert to standard form, multiply P transpose through the entire equation. So P, that gives us P transpose MP Q vector acceleration as a function of time plus P transpose K P Q vector as a function of time is equal to P transpose F vector. Yes. That makes sense? Just multiply P transpose through the whole thing. That's all we did. So if the modes are normalized, P transpose of MP is equal to the identity matrix I. Right? So I is the identity matrix, and let's go with Q. Okay, so if I is an identity matrix, right, this piece here becomes an identity matrix. That makes sense? So we can rewrite our equation of motion then as, well, let's say one more thing. And P transpose K P is equal to a matrix where omega squared is on our diagonal. And you should be able to see that from, this is the same thing of how we have always found omega, right? It's a square value of our normalized, mass normalized stiffness matrix, which is exactly what the square root of K over M in a 1 degree of freedom system. This is the square root of K over 1 M with a P in linear algebra, right? But that makes sense? Your square root of K over M is a mass normalized stiffness value squared. Pretty cool, right? Okay, so this then becomes Q double dot vector of T plus omega squared on the diagonal of a matrix. Q vector of T is equal to Q vector of T. Oh yeah, this little Q vector of T, that's just P transpose F vector, right? It's our force. It's our force in our modal space. And now we are in a modal space, right? So we have made it on our magical donkey to the modal space. We can write this, it's the same thing. I'm not changing or adding anything, but let's just break it out for a given mode, right? For a given mode, this becomes Q vector double dot of T, sorry, QI. So there should not be a vector there. QI plus omega I squared QI of T is equal to capital QI as a function of T for I equals 1 to n. That makes sense? We've seen that ordinary differential equation this entire class since day one, right? Just forget about what the terms are. Just think of the ODE. We've seen this ODE before. We know solutions to this ODE. Can I get a few head nods so we don't have to, or otherwise we go all the way back to like the first month of class. We know solutions to this. So let's just go ahead and put a solution into that ODE. Qi of t is equal to Qi initial, so QIO, cosine of omega I t, plus Q dot velocity IO over omega I sine of omega I t. That look familiar? That is just a solution to this ODE, right? And that is what we want to solve for. So the only challenge now is now we have initial conditions, right? I can give you an initial condition in a physical space, but you have QIO. How do you get an initial condition in a modal space?
Just flat?
Well, we have to convert it, right? So we have to convert from the physical space to the modal space.
Oh, so do you just do the initial condition for your physical space? And then...
Yeah, and then the modal matrix, and then a mass term also, right? So Q vector of 0, right, which is going to be all of our initial conditions for all of our modes, is equal to P transpose M x vector at time 0. Right, you know the initial conditions, and then you just transfer them into the modal space. Make sense? Q vector dot at 0, which is velocity, is P transpose M velocity 0. That makes sense? So this is going to be, I should have color coded this the whole way. This is going to be modal space. And this is going to be physical space, or let's not say that. This is your physical space. And this is how you get from one to the other.